Welcome and thanks for attending today's CTE Lunch and Learn event. I'm Dennis Spaeth, the owner and publisher of Cutting Tool Engineering. I'll be serving as the moderator of this half-hour webinar. So now let's get on to today's event, Lunch and Learn for Troubleshooting Bandsawing. It's my pleasure to introduce Jay Gordon, North American Sales Manager, Saws and Hand Tools for the LS Starrett Company. Jay has more than 40 years of industry experience, and he's been with Starrett for the past decade. He's also the author of Troubleshooting Bandsawing, the article featured in this month's issue of Cutting Tool Engineering magazine. This is the article that appeared in this month. And before we jump into the questions submitted by our attendees when they registered for today's event, I want to thank the LS Starrett Company and Jay for sharing your expertise with our audience. Jay, can you take a minute to talk about why you made the commitment to write this article and then agree to be here today to answer audience questions?
Well, thank you, Dennis. I appreciate that. Agreeing to the article was easy. As you said, 40 years of doing this, and the sad fact, or the good fact, however you want to look at it, is that bandsaws are basically all I know. Especially in the past, they've kind of got a bad rap. You hear it's just a saw type thing. But I can tell you that over the last 40 years, and maybe more importantly, over the last 10 or 15 years, things have really gotten better and better at more precise tooling, more precise cutting, more precise or faster production, those types of things, along with the saws getting better. So I wanted to take a moment to at least say, okay, everyone's going to have a problem with some of this stuff. Let's give some high level ideas to the people so that they know that bandsawing is important, especially for me, of course. But if you think about it, bandsaws are the first thing the metal hits. Before it goes on to the mills, the drills, the whatever it is, it's got to be cut, whatever that metal is. And if it's wrong there, you're starting from the wrong position and, moving forward. So whatever I can do, and, my little piece here to help, I am more than willing to do.
Okay. So rather than recap the information covered in the article, which is something we have done in past webinars, today we're going to go directly to the Q&A session in an effort to get to all the questions that were submitted for this session when all of the audience registered for this event. We will try to get to as many questions as possible, and if we run out of time, any questions submitted during the live event, Jay is going to be available to respond directly to you after the official recording of the live event is over. So let's just get right to it, get to the first question. So Jay, there you have it. What should be taken into consideration about the number of teeth per inch, and what is the optimal number of teeth to have in the cut at any time?
Well, generally, the teeth per inch is determined by the size of material, not necessarily the type of material. So, a 2-inch piece of bar versus a 10-inch piece of bar. Bottom line, no fewer than 3 teeth in the material at all times, and typically no more than 24. For a nice round medium, somewhere around 12 to 14 teeth is optimal. Now, what I will tell you is that there are exceptions to every rule. For example, if you're cutting something really soft, you can actually go coarser because you need the gullet capacity and you want to cut it fast. And if you're cutting something hard, you can actually go a little bit finer tooth in order to get more cutters and you're not filling up the gullets. So the key between both of these questions is to match your tooth pitch to the size of the material. So if you have we'll go easy here, a 1-inch piece of material, you don't want a 1-tooth blade. As you could think about that, it would just literally rip the teeth off the blade and nothing would do it. So you have to have at least 3 in there so that the teeth are all capable of taking a chip and it works smoothly. Too coarse and it's going to start slapping and causing you issues. And on the other side of that, If you have too many, the teeth will tend to fill up no matter the material if you have too many. And what happens then is then the teeth just wear out as opposed to really cutting. You end up filing your way through it is what it amounts to.
Okay. Well, let's go to the next one. How do we determine the right tooth profile to use?
So profiles are pretty much determined in the manufacturer's catalogs as well as ours. Basically, what you're looking for is what type of material you're cutting. Is it a solid piece of bar? Is it a structural, a tubing, a channel, an angle, things along those lines? Is it small type stuff? You have a lot of different options, whether it's, and for this discussion, we'll talk about bimetal, not so much carbide because there's a lot more options in carbide as well. But for your bimetal, your everyday type cutting, even some production cutting, that type of thing, most of the manufacturers will push you to the right blade. So if you look at it, you're cutting a solid piece. You want something that's relatively aggressive. You want something that will be able to clear, has bigger gullets, will be able to clear out the chips. On the other hand, if you're cutting structural type material, you don't want to be quite as aggressive with your hook rate or your hook angle and that type of thing. And then typically when you're cutting structurals, because of the stresses that they have, you want something with a heavier set, the right to left side of the teeth going, so that it makes a wider curve or a wider slot, if you will, that reduces the issues of pinching. So generally speaking, for the profile, more aggressive for solid type materials and even harder type materials, less aggressive for more structural type materials, and then of course you have, and I'll call it a general purpose type product, which is usually has rake angles from all the manufacturers that is fairly low, maybe 2 or 3 degrees, something along those lines, down to 0. But it's good for cutting, well, everything. You can cut, some solids, you can cut some structurals, you can cut all kinds of different things. It will not be the highest production of them, but for those that need to be able to cut a bunch of different materials well, then that's your best way to go there. Did I answer that?
I think so. And there are some questions coming in from the audience, but let's take this next question here first. How do we determine the right blade feeds and speeds?
The feeds and speeds are determined by the type primarily of material. So stainless steel versus carbon steel versus alloy type steels. All the manufacturers have feed and speed charts that will tell you, where to, or at least give you a general idea of where to start your blade speed and your feed rates and things along those lines. As a general rule of thumb, softer material, faster blade speed. Think about that. That makes sense. So the hard material, slower blade speed. What you're trying to do is you're trying to get that tooth to penetrate. So if you're cutting aluminum, very soft, it doesn't take a whole lot of pressure or slow speed or anything like that to pull that chip, because it is so soft. It just, it cuts like butter, so to speak. On the other side of that, if you're cutting some type of alloy or maybe some stainlesses and things along those lines, they're a little bit harder, actually a lot harder. So you will slow your blade speed down and allow that tooth to penetrate the material and then pull the chip. So basic rule of thumb, as I said, soft material, fast blade speeds, hard material, slow blade speeds. That's basically how it goes. Now, as far as your feeds and feed pressures, let me make a comment here. There is a difference between feed pressure and feed rate. So feed rate, if you have a saw that has both of them, most of the bigger production type saws do. Feed rate is your speed, how fast the head is coming down or going forward, whatever the case may be. Your feed pressure is how much push is behind that. All right. These numbers, again, well, actually in some saws, you'll see them right on the saw. It'll tell you, there'll be a gauge that says, okay, you're cutting 302, so turn the handle to this particular number and turn your feed rate to this particular number and the blade speed will go. But generally speaking, in the catalogs as well as the websites, and then, we do have like slide charts and things that will allow you to pick the number or pick the product that you're cutting and it'll say, okay, it's stainless steel, so you need to cut this at 120 feet per minute and 5 square inches a minute and that type of thing. I would also note, as we're talking about feeds and speeds in the saw world, we talk about feeds and speeds and cut rates as square inches. So anytime we give you a number, with one exception, I'll get into that later, but anytime we give you a number like 5 for a feed rate, we're talking square inches. So 5 square inches a minute of either forward progress or downward progress, whatever the case may be. Okay.
Jay, I hope you don't mind. There's a question that came in, and it kind of relates to the blade pitch. Comes in from one of our viewers right now. It says, are there any drawbacks to the variable pitch blades? Been using them with fairly good success, but didn't know if there were any reasons not to use them. No,
that's a really easy question to answer. The advantage of variable pitch versus a straight pitch. So the original blades were straight pitch, so a straight 3-tooth or 4-tooth per inch and that type of thing. So back in I want to say it was the 70s. They came out with a variable pitch blade, so a 3-4 versus a straight 3 or straight 4. The advantage of a variable pitch is twofold. One, it opens up the range with which that tooth pitch can cut. Every tooth pitch has a certain range on a certain material that it cuts well. So let's say if it's a 3-tooth, you can cut a 1-inch to a 4-inch reasonably well with that particular blade. All right. With a 3-4, now you're cutting from a 1-inch up to a 6-inch. So you've opened up that range with that blade will handle well and still give you good results, accuracy, production, all the other type of thing. The other one, and no one thinks about this, it cuts down the vibration, which means it cuts down the noise. Noise, vibration, whatever you want to call it, is bad on a blade. If you were to put a microscope under it while it was running, you'd see that little tooth just a wobbling, and it's metal. So eventually it's going to fatigue and it will eventually break. So if you can cut down the harmonics, all right, the noise, the vibration, which the mixed tooth does, the variable tooth does, that will improve your life as well.
Very good, thanks.
Sure.
So brings us to the how does cutting fluid factor into the sawing process?
Well, I get this a lot. So cutting fluid, to me, a guy who does nothing but saws for the last however many decades, cutting fluid is very important. I mean, it is probably one of the most important. Bandsaw blades need both lubricity and cooling properties. All right. Without those, you're generating a significant amount of heat, which is detrimental to the teeth and the blade itself. So you're going to lose life. The issues that come to play is now. I mean, originally, cutting oil was the big thing. It is, and in my mind, it's still the best. Nobody uses it. It's dirty. It stinks. It's dangerous, flammable, that type of stuff. So everybody's gone to some type of soluble oil or synthetic or semi-synthetic, and they all have their pluses and minuses. The key is to use them. If it is just dripping on a blade, it's not doing. You want to flood the zone, so to speak, so that blade is being lubricated and cooled at the same time, so the chips can get in and evacuate once they're out of the material. The other thing that people complain about with regards to cutting fluid is it's messy, and yes, it can be messy, especially for those of you that are cutting structural materials, whether it be channels or tubing or whatever the case may be. You throw your 20-foot bar up there and you throw your coolant on high and you start cutting, and the next thing you know, the coolant's down the 20 feet down the road and on the floor down there. And there's been a lot of complaints of that over the years. So what came about was, and I'm going to call it a misting system. There's several different ones out there. Basically that's what it is. It just puts a mist on the blade as opposed to having the coolant, flush all the way down. This works okay on structural materials. I certainly don't recommend it on solid materials. But if that is an issue for you, then certainly consider that as opposed to nothing. For those of you that have the little maintenance saw with no way to do a mist or a flood type coolant, something along those lines, anything is better than nothing. If you can get one of those, what do they call them, wax sticks, you know, the welders using things along those, and let it run through the blade every so often, that'll be helpful. Every little bit helps. It is a matter of, you know, not one big thing is going to solve every problem out there. It's always going to be a bunch of little things that add up to give you the best life and the best accuracy and that type of thing.
Okay, thank you.
Sure.
Okay, we're going to address the question that came in from the audience was, is it necessary to break in a bandsaw blade? And what changes are you looking for in the blade so you know when it's broken in?
Yeah. So let me take the second one first. In reality, there's nothing that you can look at to see now that it's been broken in or whatever the case may be without a magnifying glass or something along those lines. So back to the first part, and I'll work my way through here. So is it necessary to break in a bandsaw blade? So this has been going on for as long as I've been around. You know, I really don't want to break it in. It takes time to do this and that kind of fun stuff. So the bottom line is yes. Okay, and I guess in truth, it's up to you. You know, you're looking at somewhere between, and again, it depends on the situation, but you know, for nice round numbers, let's say 25 to 35% better life by breaking in the bandsaw blade, you know, depending on what you're cutting. All right. And, you know, if you think about that, I mean, if you're getting 100 square inches out of a blade, you're now getting 125 square inches. Do that over the week or the shifts or whatever the case may be, and you're saving some real money doing that. Okay. So to me, I break everything in. Okay. There are some products on the market now where they are, I'm going to use this term, they're not going to like it, but they're pre-honed, so to speak. And they say you don't have to break in the blade. Okay, I mean, if that's the way they want to go, that's fine, but I'm just old school. Okay, and you give me a blade, I'm breaking it in, and that's the way we're going to do it. Now, what does break in do? So everybody's used this analogy. If you guys have ever been around saws, you've heard this 100 times. Think of the pencil analogy. You sharpen a pencil, you go to write, it writes really well, but if you push hard at all, it after you've sharpened it and write a little bit or rub it around a little bit, then push on it, it doesn't break. That's what you're trying to find. Okay, so when the blades are manufactured, they are manufactured with a very sharp tip. Okay, and it's anything that sharp is brittle to a certain extent. So if you go into your whatever material it is you're cutting, and at full speed, your normal feeds and speeds, assuming everything's correct, you know, it is very likely that you're going to start chipping the teeth. Now, if you chip the teeth, obviously your blade life goes down, eventually your production goes down, and you've just wasted a, you know, $20, $50, $100, $200 blade, whatever the case may be. So if you go in it with the attitude that I'm going to get this thing broken right, and I'm going to get the best life, production, accuracy, everything else I can, it's a much better way to go. So while we're on this, if you don't mind, Dennis, breaking in a blade, technically, it's going to depend on the material. You should always break it in on a solid. Most people don't, because if they're not cutting solids, they're going to cut structural. Okay, so I mean that is what it is. The key here is to make the blade work less hard. So let's say that you've got a blade speed of 200 feet per minute for whatever it is you're cutting, and you have a pressure rate at 100 pounds of pressure for your normal cutting. So when you break in a blade, many people will say, okay, well, I know I'm supposed to cut everything in half. All right? So they're going to take that blade speed and knock it down to 100. They're going to take that pressure and knock it from 100 down to 50. Now think about that. Okay, the blade is technically, or at least, working as hard as it was before, because now you've slowed the blade speed. It's going to take a bigger chip, actually. You've got the pressure down. So the blade is actually working as hard as it was before, at least. What you want to do when you break in a blade, one, like I said, if you can do it on a piece of solid, you're much better off. But regardless, anytime you do it, you're much better off. So in the case of the 200 and the 100, you leave your blade speed basically where you set it for that particular material on production mode. Okay, so if that's 200, fine. You may go plus or minus 10. There may be a little bit of squeal or something to get it out of it. Then you back off your feed pressure by half. Okay, some materials may be only 25% because they'll work harden, but generally speaking, let's call it half. That way, your blade is still going and is still set for the type of material, carbon steel versus stainless steel, and the feed pressure has lowered, so the blade is not pushing into the material as hard, and it's not near, or the blade's not near working as hard, and that's the key. So basically, what you're trying to do is you're trying to get those tips. It sounds wrong, but you're basically trying to get those tips rounded or honed, whatever word you want to use, so that your life will go up significantly.
And if we're looking at that slide that's on there right now, you're basically describing that middle picture. When you're talking about what you're trying to go for.
Yeah, I mean, again, you're not going to look at this and look at the blade and say, okay, now it's perfectly honed or rounded or something along those lines. It's going to be a case of in theory. We can get you charts and numbers for every type of material. You have to break it in for X number of square inches and things like that. So I don't know anybody that does that, obviously, but I mean, we can help them out. That is not a problem. My suggestion is give me 15 to 20 minutes of actual cutting, not the material coming in and out, not the head going up and down, not adjusting, not bathroom breaks, none of that kind of fun stuff, of actual cutting. All right, and that'll get you in the ballpark on most materials.
Okay, thank you.
Sure.
Okay, what materials are considered the most challenging to cut, and what are those challenges?
Well, I guess the easiest way to answer this is in the last, we're going to call it 10 years. Well, I guess we should call it 20 years. I'm really old. But materials have changed significantly. All right. When I started, finding a piece of alloy, something was limited to the very big places and a rarity. Nowadays, even some of the smallest places are starting to get into what I would consider, space age alloys, nickel alloys, and that type of thing. Those are typically the most challenging to cut. So you're talking Castalloys, Monels, Inconels, all those L's and different types of alloys with the high nickel and high temperature. They're difficult because they are hard, number one, and you have to penetrate. If you don't penetrate, then you end up work hardening, and that makes that hardness of the original cut even worse. So you have to make sure that your feeds and speeds are pretty much 100% correct at all times. Typically it is also a very slow cut. I was at a place a couple years ago and testing some new product, and it was a 66-inch bar, solid bar that we were cutting. Well, 3 days later, and they were happy. Okay, 3 days later, we finally got through that thing because it was some kind of really weird alloy and that type of thing. So anytime you get into the unknown, and nowadays with all the different alloys, people have proprietary alloys, and you're not really sure what you're cutting. It can be difficult. So the carbon steels have been around forever. The stainless steels have been around forever. I mean, those types of materials are well known, and we have a lot of information to go through as far as what feeds and speeds and that type of thing. But when you start getting into both the proprietaries and all the alloys, while they have been around for quite a while now, there are so many different versions. It is difficult to be sure exactly what you're cutting, and then it is a key to watching the chips like it is on anything else to make sure that you're in the right ballpark.
You want to talk about the industries that this would
Sure. I mean, and that's basically what I said. I mean, the aerospace industry is obviously very big, and that's when I say aerospace, I mean that could be rockets, that could be airplanes, it could be all the people that are servicing them. The truth of the matter is, uh, with very few exceptions, like maybe fabricators that are primarily structural and things like that, you're going to start finding these materials in different sizes, obviously, not the 60-inch type materials everywhere, but you're going to start seeing these materials in darn near everyone's shop. Some of the smallest shops I've been into, they're cutting, a 3 or 4-inch round of Inconel and having problems. Well, because they've never cut it, and they don't have a machine that really is designed to provide what's necessary to cut that. So at this point, yes, there are some special industries that deal with this stuff, primarily aerospace, some automotive, that type of thing. But I mean, it's coming. If it's not already in your area, it's coming. So.
Thank you. Next question you have is, what factors are involved in selecting the right bandsaw blade for a particular application?
Good question. And I think, if you review everything that's been said, you're going to see that we're pointing in that direction to begin with. So obviously the material, okay, what it is you're cutting. So then you know the speeds and feeds that you're going to cut. And then you have to decide what it is that you want out of the operation. Do you want, okay, let me back up. Everybody wants everything. Okay, I get that. You want the best production, the best, cost, the best speed, the best accuracy, the best. I get that. Okay, but in truth, you're going to get 1 or 2 of those, and not all of those. All right, we can cut certain materials really fast, but the blade's not going to last. Okay, if that's important to you, then that's what we do. So the key here is to determine what you want to do. If you're cutting something, and you're striving for 100 pieces on the floor per blade or whatever it is, then you will have to determine, okay, do I stay with 5 metal? Do I go to carbide? Do I go up to M51? Those type of things if you're not hitting those numbers. But when you come in at from the front, one, obviously make sure that whatever product you're looking at is available in the size blade, because some machines, or most of the larger machines, only take a certain size, 1 inch, 1.25 inches, 1.5 inches, whatever the case may be. Make sure that it's available in that. 2, make sure that you've already discussed what you're doing for tooth pitch. All right, we talked about the 3 and the 24. So if 90% of the stuff you're cutting at the 4-inch, you don't want a 10-14 blade. You want something a little bit coarser to do that. So you have to do that. Lastly, we talked a little bit about the profile, and I don't really get into profiles a whole lot when we're talking in the catalog thing, but all the catalogs will point you to the right direction if you're looking. So if you're cutting a solid, you want something aggressive. All right, so let's call it 10, 12, 14 degree positive rake. If you got something that's structural, you want something, we'll call it middle aggressive or less aggressive. So probably 5 to 8 degrees positive rake, somewhere in that general vicinity, and a heavier set. All right. And lastly, what problems are you having now? If you've cut this material and if you're having a pinching issue, perhaps you didn't have a heavy set blade, and that will solve the problem completely. If you're in a structural material, if you're having a different issue, that's what we have to bring. And there's people out there to help you. Okay, I mean, there are a lot of people in the field that will be more than happy to help you and say, hey, your speed's wrong, or this is not the particular blade for that application, and you really need to move over. So if you got a blade that was basically a profiles type blade, a heavy set type blade, and you were cutting solids, would it work? Yes, it would work. Okay. But it would be slow and wouldn't last, and all the rest of that kind of fun stuff. So knowing up front what it is you expect from that particular blade, or what you expect from that cut, I should say, will certainly point you to the right direction as far as which blade to go.
Okay. So when is a bimetal blade the best option?
Nowadays, okay, back up just a hair. So the first blade was carbon. All right, everybody used carbon to cut steel. All right, so keep in mind, carbon will cut steel. Nobody uses it for that anymore. Your next step up was bimetal in several different versions. Nowadays, M42 is usually the starting high-speed edge and goes up from there. And then, of course, your next option is carbide. Generally speaking, if you're cutting steels, even stainless, even titanium you can cut with a bimetal blade if it's not a big high production type thing. Generally speaking, for most shops, if they don't have a saw that is in really good shape, let's put it that way, or has a lot of vibration, or maybe is not meant specifically for a carbide blade, it's really not a good option to put a carbide. So your next option is bimetal. If you're cutting metals of any kind, your first option should be bimetal. All right. Which bimetal, we'd have to determine by what you're cutting and that type of stuff. The bimetal advantage over, and I'm assuming we're talking about carbide here, is and it's going to sound weird, but bimetal advantage is it's softer. Okay, so let's say your teeth on the bimetal blade are around 69 Rockwell C, where a carbide blade's like 100 Rockwell C. Well, that's great and that's good, but harder is more brittle. So if you start cutting tubings and channels and things like that, you're very likely to break the carbide blade, but you're not going to break, or usually won't break, the bimetal. So whenever we go into a shop, or whenever someone asks me, the first blade I put on the table is a bimetal blade. Unless they come and say, I'm cutting some really hard stuff, I want it out as fast as I can possibly go, and I want the blade to last as much as possible. Then we can discuss carbide, assuming their saw will do what needs to be done. But bimetal is the most common. It is the bread and butter of the metals industry.
Very good. We are getting close to the maximum time here, but I think we can get through the rest of these questions that we had in advance. When should carbide tip blades be selected? And I think you just were touching on that.
Yeah, I was just in there. I mean, if carbide blades are one for solids, okay, you can get away with some heavier structurals and things like that. For general, let's just say solid material. It will cut soft stuff. I mean, people cut aluminum with carbide blades, and they cut all those alloys I just talked about, your Inconels, Monels, and all those kind of fun stuff. Carbide's advantage is its hardness. All right. Carbide's advantage is production. All right. If you have a production saw and you need parts on the floor as fast as humanly possible, then carbide is going to be the way to go. And there's a lot of different versions of carbide depending on what you're cutting. But generally speaking, highest production, longest lasting. Okay. And I will add most expensive. Right, so you have to make that equation between bimetal and carbide and all. The last thing I'll say about carbide will fit, assuming it's available in whatever width saw you have. Carbide will fit on any saw. I mean, it's a bandsaw blade welded to length, no issue as far as that goes. But really shouldn't be run on any saw. The saw manufacturers out there manufacture actual machines for carbide specifically. They're very heavy, very stout, no vibration, that type of thing. As we talked about a little bit with the mixture, the variable tooth that someone asked about, vibration is killer, and carbide doesn't like vibration, so that would be a problem. But if you're looking for the best of production and the best of high performance, life and smoothness and that type of stuff, and you're cutting a solid piece of material, absolutely give it a shot.
Okay, great. So this came in from a shop in advance when they registered. They asked about, they have 4 fixed speeds on their saw, and they're wondering about other ways to compensate when they don't have an exact match for the recommended speed.
Well, yeah. All right. So some people have 3, some people have 4. Pulleys or whatever the case may be that they use. The fact of the matter is there's no real way to quote unquote compensate. What you can do is, of course, put your pulley or put your speed as close to where the material is supposed to cut. And then you're going to have to watch your chips depending on what you're cutting. Now, you may be able to, if you're going a little fast, maybe you can push a little harder, or let the saw drop faster, whatever the case may be on your type of saw. and that'll get the chips up to where they want. If you're going, a little slow, you can back off on your feed pressure and that type of thing, and that will help. So you're compensating to a certain extent. It's very difficult. You really need to be relatively close as far as feeds and speeds go in order to work the best. But I'm sure you've been doing it for a while already, so it's working. Just find out which speed is the closest to where you need to be, and most importantly, be changing it. Don't just leave it on pulley number 4 because that's where the guy before me had it on and he was cutting carbon and you're cutting stainless. That would be the problem. What's the proper choice for vertical bandsaw blade all around? Okay.
Yeah.
Okay. One of my pet peeves here. So everywhere I go, everyone wants, and this has gone on forever, everybody wants one blade that will cut everything. Unfortunately, no such thing. Okay, I mean, not and do it well. Let me rephrase that. Okay, so vertical or horizontal is immaterial as far as what type of blade you use and that type of thing. If you're cutting steel on the vertical, in this case, a bimetal blade of some kind, and that's going to depend on what kind of vertical. I mean, there's big verticals that use 2 5/8 or 3 1/8 inch wide blades, and there's also verticals that use an 1/8 inch blade. So a lot of it's going to be dependent on the saw. In a small shop, I will tell you the two most popular blades, and they're kind of split. If you're cutting a little bit to the bigger size, probably what we call a 610 pitch. If you're cutting mostly to the smaller size, it'll be a 1014 pitch. But here's the problem with either of them. You're going to come up to a point where, okay, I've been cutting nothing but say 2-inch material forever, and now this guy comes into the shop and has a 6-inch piece of material, and neither one of those blades is going to work. Okay, it's going to be just way too fine, and you'll be upset. Let me leave it that way. Okay, so tooth pitch. See what you've got. Try to put it in a box as, okay, everything's from 0 to 1 inch, or everything's from 2 to 6 inch, or whatever it is, and then base your tooth pitch on that, and that will at least do 80% of your product. And then when you get the oddball, then you get another blade and move from there.
Okay. There's just a few more questions, so I'm gonna extend this a little bit so we can get to all of them. Technology makes it easier to be more precise, but do you have any advice for being the most precise on more manual, older saws?
I started with manual and older saws, so I'm an older guy, so I love older saws. I'm good with all of that. The key to any of them, whether it's an older saw, older car, older whatever, is maintenance. The key is the guides have got to be tight. The arms, I've seen more than my share of arms that are holding the guys wobbling. Well, that's not going to work. The trunnion bushing that holds the head up will wobble. The key is to make sure everything is as tight as when it was when it came from the thing, and then reason. And by reason, I mean if you're normally going through a piece of, in this case, it looks like a big chunk of 10-inch material or something. If you're going through that, and in days past you were flying through it at 10 square inches a minute and just having a great heyday, and now as the saw has gotten older, it starts to walk and you start having all those problems. So again, checking the guides and everything else that's around the blade will certainly help. But keep in mind, there's a lot of other things that could be going on. Your cylinders could be leaking, so your actual have it set at 10 and it's actually doing 15 square inches a minute or whatever the case may be. So make sure you time everything, and like I said, take it easy. I mean, it gets to a point, well, stay in that box that I talked about earlier with regards to good feeds and speeds for each material. Stay on the low side of that box, so the slower side of the box, and that will do you well.
Hey, what's a good blade for cutting the chrome-plated induction hardened round?
Chrome-plated induction hardened round. This is a fun one. There is a special blade for cutting chrome-plated induction round. It's typically a negative rake blade. For Starrett, we call it our advanced CS. And I know it sounds kind of counterintuitive to have a negative rake blade, but the carbide, I'm going to use a technical term here, the carbide bashes its way through, okay? And that's what happens. The material inside is typically very soft. Let's call it 1025 or something along those lines. The other thing I would note is that, and I made mention of this in one of the first slides or whatever, this is the only material that we don't measure cuts by square inches, or excuse me, feet rates by square inches. With this particular material, you're going to run your blade, let's call it 300, 325, 350 feet per minute, somewhere in that general vicinity. And then you're going to cut linear inches. So if it is a 1-inch piece of material, you're going to cut in 1 minute. If it's a 2-inch piece of material, you're going to cut in 2 minutes, et cetera, et cetera, et cetera. Because like I said, the stuff in the middle is soft. So basically you're banging your way through it, for lack of a better term, and getting it. There will be a certain amount of chips generated. Negative rake blades do generate chips, by the way. There are materials that are pretty close to the same hardness of inductive chrome rod all the way through, and they do use a negative rake blade, and it does generate chips. So it's there, but this particular thing is one of the oddballs, but fun to cut.
How does a new operator get up to speed, and what are the basics you recommend every operator know before cutting?
I think pretty much everything we've talked about are the basics of what the operator should know, to be honest with you, Dennis. At least, let me back up a second. Let me throw this out here. I go into, or people go into a lot of places, and the operator doesn't know what kind of material he's cutting. Meaning, they gave him a piece of steel and said, cut it. That doesn't work. Okay, you need to know the difference between 1040 and 4140 and all those types of things. All right, so that's one. Number two, you need to get your hands on some type of speed and feed chart, whether it's in a catalog or a slide chart or an app or whatever the case may be, so that once you've identified that particular material, you can set your saw up to that. And I will say that it is always good for a new operator to talk to the old operator, because the old operator is going to know what's working and what's not, and what he's had to finagle, for lack of a better word, to make work. Because you may walk up there as a new guy, turn your feeds and speeds perfectly compared to the book, and now the saw is still screwed up, and now blades, teeth, everything goes everywhere, and it's a problem. So the key, of course, like I said, know the basics, get your hands on the feeds and speed charts, make sure you know the material, not just the size, not where it came from, the type of material. All right, and that will start you down the road.
Before we close out, we did get one more question come in.
Okay.
This same individual who was wondering about our pre-welded blades, any better or worse than coiled blades? Derek is saying he generally buys the coiled blade material and welds it himself, and it seems more cost effective.
Yeah, and I think that's a decision that everybody wants or has to make. I mean, as you know, Starrett is the manufacturer here in the States. We sell a lot more welded blades than we do coil stock, and that would be true for pretty much everybody in this industry. Back in the day, every distributor had a welder. Now, not so much, and most of that was due to costs and that type of thing. If you've got a smaller bandsaw, or maybe one of the bigger Duals that had a welder on the side of the bandsaw, coil stock is a much better way to go. You're welding 1/8 inch, 1/4 inch, 1/2 inch material and that type of thing. No biggie. So that is purely personal as far as how cost effective it is. The advantage, of course, is if you break a blade that's welded at any factory, it's covered if it's broken in the weld. Okay, I mean it was an issue, and they'll make it right. We'll make it right. And you'll be good to go. So if you break it because you welded it, well, there's 10 foot of scrap or whatever the case. And then scrap's the other thing too. never do you burn up the entire coil. There's always scrap left unless you start welding 2 or 3 times in a blade, and that's problematic too.
Okay. Well, that pretty much concludes the webinar for today. Before you go, please complete the short feedback survey that'll pop up after I end the live event. And just as a reminder, a recorded version of this webinar will be available within 24 hours. And now I want to just say thanks to Jay and the LS Starrett Company for taking the time today to share their expertise with us and with the audience.
Thank you, Dennis.
Appreciate everybody really attending. Go ahead.
So no, I was going to say thank you. I really appreciate the opportunity here. So I had a good time.
It was a lot of information in a short amount of time. We went over our time limit, but I hope everyone was okay with that. I think we got to just about every question that came in advance and a couple that came in during this event. Appreciate it.
Good.
Take care. Have a great rest of your day.